thank you very much for inviting me here and at IBS. It's a very nice place. And thank you to the camera crew, always reliable. So today I want to talk about permutations. I think pretty much everybody here is mostly working with graphs, maybe some matrices or hypergraphs. And so I would like to convince you that permutations are not that different from graphs. And sometimes they are much nicer. And the reason they are nicer is something called twin width, which may happen to be my specialty by some strange coincidence. So let's start with permutations. Okay, I won't say what is a permutation because this is stupid, but how I represent them. So if you ask a random person in the street what is a permutation, they will probably tell you what. But if it happens to be a mathematician, I think they will tell you it's a bijection from the integers to themselves. So this is how I write integers from 1 to n. And this isn't the most convenient, in my opinion, definition when you want to do combinatorics. So what I prefer to say is that, okay, so you have this set n, and it has the natural ordering, and now you can define a permuted ordering, which is x is smaller than y in the permuted order, when you just compare the images. Okay, so if I want to say that more abstractly, I have a set of vertices, a first ordering, a second ordering, which are binary relations. So for me, this is starting to look like a graph. I have vertices, binary relations. Okay, there's two of them. They are orders, not edges, but yeah, pretty much the same. So if I want to really draw this as a graph, I would say I have some vertices. Okay, let's make, I don't know, permutation 3, 1, 4, 2. Let's say the first ordering, I will draw it in blue, and I will put it on top. So let's say this is just the left to right order. So every edge is going this way. And now the second ordering, well, here it would correspond to the numbers I just drew. So 1 is the smallest, it means every edge will go out from 1. And then you have 2, which is the second smallest, so edge is going out like this. And the last one will be this. Okay, obvious problem with this is unreadable. But it's the graph I want to think about. Now here's how I actually want to draw the permutation. Let's do the same permutation. What I'm going to do is have 2 copies of V, one with the first ordering, and one with the second. And then I just put the matching between them. So the first vertex in the first ordering, like let's say this is 1, 2, 3, 4, from top to bottom to top. So the first vertex would be mapped to the third, second to the first, and so on. So this is a readable representation of the permutation. But again, if I want to think about it as a graph, this is the actual graph I care about. Now, if you have this representation, okay, what might you want to do with permutation? Maybe you want to take the inverse. Then that's very easy. You just swap the roles of the 2 orderings. Or if you are in here, like, what this diagram says is this is the input of the function, and you follow the matching to get the output. So if you want the inverse, you just flip it. Maybe you would like to compose it with a second permutation. I'm not sure, this one, for instance.
By the way, when you wrote the vertices on the second column, did you write 1, 2, 3, 4 on with respect to this 3, 1, 4, 2?
So here the way I think about it is this is the domain of the function, this is the image, so this is saying I'm mapping 1 to 3,
Okay.
which is the same that I have on top. But if you want the relation between this and this representation as two orderings, an edge in this diagram corresponds to a vertex in here. And if I look at the left-hand points, I take the vertical ordering, this would be the first order. And if I look at the right-hand points, I get the second order.
But you choose the first one, like so every vertex is mapped to the image. Every vertex on the left column is mapped to the image of.
Yes. So yeah, I was saying if I want to compose two permutations, let's say this is my second permutation. Okay, with this diagram it's quite easy. Like you just identify these, and now you need to follow the path from start to finish. That will be your permutation. If you want to write it with this, what you need to do is say, I have somehow managed to write the two permutations on the same vertex set, and so that the middle ordering coincides. Let's say these are my two permutations, then the product would just be you keep this ordering and this one. Of course, when I have this, I treat everything up to isomorphism. So I can always rewrite my permutation so that these two things are the same. Okay, so these inverse compositions are, like, say, the usual permutation, usual operations, which would actually work better if I wrote everything as functions. But the reason I did not write it as function is the next definition, which is a pattern. And now this definition is going to be completely obvious. It's I take a subset of vertices, and well, I have an induced subpermutation, I could call it. Just I keep the same ordering. I take a subset of vertices, and this is I will write it like this, but this is it's a pattern of my starting permutation, the order 1, order 2. Everything's clear so far? Okay, now.
So you take a proper subset, and then that's just
Yes.
called the pattern. It's a permutation, right?
Yeah, it's
permutation.
technically, yeah, could even be equal. But pattern is the same as an induced subgraph once you have this definition, which is really what I'm trying to say. So what do we do usually with induced subgraph? We forbid them. And I'm going to do the same with patterns. So I can define f of tau, if tau is a permutation. It's the set of permutations sigma, which does not contain tau as pattern. And okay, instead of saying forbidden, the usual terminology for patterns is avoid. So it's the set of permutations which avoids tau. Now, okay, if it were a graph, imagine you take H to be a random, arbitrary graph on 10 vertices. And you look at f of H, the class of graph which don't contain H. Well, good luck proving anything useful about this class. Right? It's like maybe you would have Erdős-Einhal, but that's only a conjecture. There's not really any result, or very few of them, which hold for the class of graph avoiding H for an arbitrary H. And this is where permutations are different. I want to tell you that this class is quite nice, no matter the pattern tau which you pick. So, okay, I'm going to present a few results. And the first one is about enumeration. So this is relatively, not that old. It's called the Stanley-Wilf conjecture. It's from around the 80s. There's no precise date. I don't think there was any paper of either of them which stated this conjecture. It's like something which was stated in informal settings, and eventually some papers from someone else said that they said the conjecture and so on. So there's no precise date. So the conjecture is, you take any pattern tau, And I want to look as you go at this class. And I want to say that there's not too many permutations. So there exists some constant, which depends on tau, such that, so I look at permutation which avoid tau and of size n. These are permutation of size n. I realize I should provide you an example before going to this. So let me close this conjecture and make an example first. This. Oh. Wrong order. So, yes, actually I have an example which will be very useful later. Who knows about cographs? Okay. So I'm going to do cographs but with permutations, and I will also define cographs for those who don't know it, so don't worry. So let me make two columns. There will be, this is cographs, and the cographs of permutation are called separable permutations. So both of them have a very unhelpful definition by forbidding some things. So for cographs, you want to forbid P4, P3.5, as we've been taught to say. So these are cographs, and for permutation, okay, you need to forbid not one but two patterns, which are 3142, yeah, that's the one I drew, what a coincidence, and 2413. So, yeah, let me just redo it here. So this is the first, and the second one is the inverse. Okay. So this is a cute definition, but it doesn't give any intuition about how they actually behave. So then there's a definition with operations. So for cographs, it's the graphs created by disjoint union or complete union. So disjoint union is just you have two graphs G and H, and with disjoint union. Complete union means you add every possible edge between them. The equivalent for permutation, what would be the most obvious way to combine two permutations is, let's say again with this representation, let's say you have your first permutation, call it sigma, and your second permutation tau. Well, I do actually exactly this drawing. I put one on top of the other. So like I will split my domain in two halves. The lower half is mapped according to tau, and the upper half according to sigma, or vice versa. I don't care. So this I would call a direct sum. And you can also make the skew sum, which means you swap the images. So now, so you still split the domain and the image in two, but the lower half of the domain will go to the upper half, and vice versa. So they cross. So, theorem, the permutation which you can create with just these two operations are the same as this. And then in both cases, it can be quite nice to draw them as, like you can make it into a tree, where every node would be labeled 0 or 1. And the label tells you which operation you should do. So the leaves will be the vertices. So if it's a cograph, then 0 means disjoint union, 1 means complete union. Or for permutation, it will be direct or skew sums. Okay. So, end of the example. Any questions? Let's go back to this conjecture then. So I was saying,
I have a question.
yes.
So is there a reason why you prefer to use the two-column graphic representation rather than permutation matrix?
I don't know, I find it easier to, okay, permutation matrix, it's not easy to draw the product, but I guess it's not that good of a reason because I don't do that very often. Yeah, permutation matrix is also very nice for permutation.
So this is useful for product, and you do product a lot.
I will do product at the end of this talk a lot, but right now I'm not. So yeah, standard wave conjecture is about enumeration, and okay, if you take for instance this separable permutation, how many of them do you have? Well, this encodes the permutation, only these 0, 1 trees. So okay, I don't know the exact number of trees, but it's exponential. Okay. So this quantity, like this is the number of permutation avoiding tau with n elements, is going to needs to be exponential in n at least, and the conjecture says that actually it is at most exponential. Like there's still a big gap between exponential and all the permutation, which is factorial. So somehow another way to state it is, if you take a class of permutation which is closed under patterns, either the growth function, like the number of permutation of size n, is factorial. That only happens if you have every permutation, or you avoid one, and then you are much, much smaller than that. You are just exponential. Okay. Let's leave it like this for now, and continue with a different conjecture. So now I'm coming back to the talk of Guillemot-Marx a few weeks ago. Someone, I think it was Tony, asked if you remember the paper of Furedi and Heinal with all the false conjecture. So I think you asked if there were any true conjecture in that one. And yes, there's a very important one. So let's Furedi, Heinal. It was in 92, I think. Yes. So if you, okay, let me make a small apartheid here. Yeah. Let me just recall what Gabor was talking about. So for him, the patterns were matrices. So you had matrix, I don't know, matrix P, N, and he said that P is a pattern in N. It's a submatrix, and also you are allowed to forget some ones. So Jung mentioned permutation matrices. It's very nice because of the terminology is well designed. The notion of patterns match, which means I can define the. Okay, so tau is a pattern of sigma if and only if the permutation matrix of tau is a pattern in this sense of the permutation matrix of sigma. Permutation matrix, just to recall, it's there is a 1 at position I sigma I. So Gabor was talking about acyclic patterns, which is you have a matrix, you make a graph where you connect two ones if they are on the same column or row. He wanted that graph to be acyclic. So here my patterns are permutation, which is a much stronger condition. So then with this pattern, he was looking at the extremal function. And he wanted to say that this function is something like n log n, or, okay, that didn't work, but these kind of things. And here, this conjecture, which is about permutation, well, says that the extremal function for a permutation pattern should just be linear. big O depending of tau, of course. So this, just to clarify, it's this extremal function, exactly the one he was looking at for matrices. It's the maximum. So here's the true conjecture. I want to do this proof because it's very nice, quite simple. Yes, it's the only proof in what I want to talk about, which I can do without hand waving. So let's do a proof. So we have the matrix N by N matrix, and it avoids tau. So I will draw my matrix here. Now what I'm going to do is partition it equally. And these will be blocks of size k squared, where k is the size of the pattern which I wrote. So so this I will call a cell. A cell is a square of k squared times k squared. And same thing vertically. Okay, let's call P this partition. Partition of two blocks of size k squared. And I can define a quotient matrix, and divided by P, which will be of size n over k squared. And it's just, this is 1 and 3 of the quotient matrix. There's a 1 if it's not all zeros. So, first important fact, the quotient matrix avoids tau. This is both completely obvious and non-trivial, because it only works because the pattern is a permutation. This fails if you have a pattern which isn't a permutation. So, by induction, okay, I mean, I won't even write by induction, but the number of 1 in this matrix, by definition, is less than the extremal function for n over k squared. And then I will do some induction using this. So now the idea is to split the cells into two kinds. There are some with a lot of ones, and I will show that there are few of them, and some with relatively few ones, and there I will just use this bound. So precisely the... Okay, let me pull this.
There's one more board behind me.
Yes, but I would like to keep this up. I don't want to have it all the way down. So I will distinguish three cases. So I have a cell C. Remember the cell is the small square k squared by k squared. And I have three cases. It can be tall, which means there are k, at least k, non-zero lines. To be something like, let's say this is tall. If I can find a one here, maybe something like this. These lines, these are the non-empty lines, and I want at least k of them.
You don't want to mix a column and row in the non-zero line?
What do you mean? So if they are all on the same column, that's fine. This would also be tall.
So line just means row, or?
Yes, a line and row is the same for this, sorry.
Ah, okay.
So if one row is completely occupied, then that's not tall.
That's not tall, but it will be wide instead.
Let's see.
Wide. Column. So line is a row and...
So let me make some more examples.
Line.
This is tall,
Line is row.
but it's not
line
wide.
is row.
Okay, I think Andrew is confused by lines, so I will put row instead. Sorry. So this is tall. There are many non-zero lines, but there's only a single non-zero column, so it's not wide. This, like for k equals 3, this is both wide and tall. And let's say still k equals 3, then this, if I make a nice square, this is neither of them. Like this is the worst case of neither tall nor wide. So this is the third case is neither. And the first obvious remark is that if I'm not tall, so there's at most k minus 1 non-empty rows, and I'm also not wide at most k non-empty columns, then the number of ones in this cell is at most k minus 1 squared. So, okay, I should put okay, I will put a total here. If I want to count the total number of ones in the neither cells, then it will be this times the number of non-empty cells, and for this I know I have this form from the quotient. And you notice here I reduced the size by a sum factor, k squared, and I multiplied the result by a smaller factor, so this is good. This is a good start for a linear recurrence. Okay, then there's wide and tall. What do I do with them? Well, if your cell is wide, the number of one. Okay, no, sorry, never mind. That's not what I want to say. I'm not going to try to be clever about the number of ones in a wide or tall cell. For all I know, it might be just full of ones. That's not an issue. What I'm going to say instead is look at all this block, like a block of columns. So I have a bunch of cells, and some might be wide. How many wide cells can there be in there? So, in a block of columns, I claim that there is at most k times k squared choose k wide cells. Why? Imagine you have this number. So what is this k squared choose k? It means this block, there are k squared columns. A wide cell needs to choose k of them. So if I have this number, I can find k of them which use the same columns. So then I end up with something like this. I have k of the columns in here, and k blocks, like maybe this one, this one, this one, and in each of them, every column is occupied. And now you can check that you can find any pattern of size k in this. So this is the number of wide blocks in one block of columns, or wide cells, sorry. So if I look at the total.
So you can
Yes,
find
sorry.
any pattern of size k?
Yes. Okay, so I should do that quickly. I
And
want
you
to
can
find my
have a look.
pattern tau. So in the ith column, I will go to block, I'm not sure, let's say this is sigma I, which is equal to, sorry, tau. Tau is the pattern I want to find, which is equal to 1. And I will keep this one at the intersection. I do that for every I. This gives me my pattern.
I see. So you pick one from each block. Right?
Yes. So the more abstract way to say it is here what we have found is a grid, where a grid means some partition. No, so this was a partition into equal parts. This isn't. It's a partition into very unequal parts. But a partition into k blocks of rows, k blocks of columns, such that every cell is non-zero. And if you have a grid like this, you can find every pattern. So back to my function. Now I have for the wide cells in total. Okay, first I have k to a fourth, that's the number inside one cell. Then this, so k squared through k, which was the number in one block of columns. And finally, there's the number of blocks of columns, which is n over k squared. Okay, and I add times 2 because it's the same with tall cells. But I mean, none of this matters. This is disgusting, but it's just something which depends just on k. I don't care about it. So in the end, I end up with the extremal function is bounded by this thing, which was the important part, which is linear. Plus some function of k times n. So this is linear. That's the proof of Marcus-Tardos. Okay, so they proved this extremal conjecture, and it gives the enumerative conjecture of Stanley-Wilf. And okay, the reason I really wanted to present this is that this theorem, this Marcus-Tardos theorem, I should rather say, is used everywhere for permutation, or at least everywhere in my talk. Every result about permutation that I know and care about uses it. So let's continue with more results which use this Marcus-Tardos theorem. So the next one I want to talk about is algorithmic. So we have this this class of permutation avoiding tau. I claim that it is nice. So if I care about algorithmics, okay, I don't, but I pretend that I do. I should show that it is I can recognize it at least, right? And this is a theorem of Guillemot-Marx. From 2016. They say that so it was well known for some time that it's NP hard to test. I give you sigma tau, I want to know if tau is a pattern of sigma. But of course this uses large patterns. So the natural question is it FPT? And they show that it is FPT and in fact even linear. So one can test if tau is a pattern in sigma in time some function of tau times the size of sigma. Okay, and now I'm going to start doing a proof by flowchart, which is my favorite way of proving stuff. So I want to use Marcus-Tardos, which means I want to find a matrix which is dense, so that I can say, okay, then this theorem tells me I will find any pattern, and in particular tau. So, okay, I should probably define the sorry, I think this is the proof. Let me add it there. So if let's say the degree of my matrix, I will say it's the average degree. And say this is the number of 1 divided by let's say the maximum dimension. Taking the maximum dimension makes it harder to have large degree, which means it's somehow a safer choice for me. So a different way to restate this Marcus-Tardos theorem is that if the degree of M is larger than some constant depending of tau, then tau is a pattern of. This will be the. This is how I want to use it. So here, where do I want to find that pattern? I want to find it in the matrix of sigma. So if I can prove that the matrix of sigma has largest degree, I find my pattern. That's not going to work very well because it's a permutation matrix. The degree is 1. But if I can find a partition P of M sigma, of a matrix of sigma into intervals, and the degree of the quotient is large, this can happen. Then I get the conclusion I want. So, here's the start of my proof by flowchart. There exists P with these conditions such that the degree is large. So this is the, okay, I already explained that branch. I have a dense, like I would call that a dense partition, and then by Marcus-Tardos, I get the pattern. You can check that the proof we just did of Marcus-Tardos is effective. You can implement it as an FPT algorithm. So this isn't an issue. So what is the alternative? Well, every partition is has bounded average degree. Okay, of course I can't check every partition, but it means I can try some specific partitions and assume that they will always have bounded average degree, because if at some point one of them doesn't, then I'm in that branch, I win. So which partition am I going to look for? Well, something which is called a contraction sequence. Okay, and I'm going to want, so a contraction sequence, it will be a sequence of n partitions. Okay, that's not a lot, I could test all of them. And this will tell me that they all have bounded average degree, but in fact I will get something much better, which is, okay, it's a contraction, so partitions P1 until Pn. Instead of just having bounded average degree, the maximum degree will be bounded. And the constant here, I think just 2 times the constant from Marcus-Tardos works. So what is this contraction sequence? It means, so somehow it means I want this partition to be at every possible level of detail of the matrix. So this will be initially the partition into singletons. So I have my matrix and I would just take every row is a part and every column is a part, which is completely uninteresting. If the quotient is the same as the matrix, of course this is sparse. That's not the, like the beginning and the start are not very interesting. This is the trivial partition, which means everything is in the, like every column in the same part, every row in the same part. And now what happens, which is interesting, is in the middle, at each step, you merge 2 rows or columns. Okay, and of course you want to keep partitions into intervals, so you will only merge consecutive ones.
2 rows or columns, right?
Yes.
Only one of them.
Doesn't really matter, but yes. Okay, and I claim that this, with a greedy algorithm, you can find one of these. So let me do it with hand waving. Right. It's a greedy algorithm, so I want this condition, I will try to get this contraction sequence, and just like try every possible contraction as long as it satisfies this condition. And now suppose I'm stuck. What happens? Well, it means I found, okay, I did too much stuff on that website. Make a new one. I have my matrix. I have found some partition. It's not regular whatsoever, but it doesn't matter. And I know that if I pick any two consecutive columns, I can't contract them. Why can't I contract them? It means if I contract where to contract them, the degree would be too much. So in these two things, I should be able to find at least this bound of the degree which I wanted once. But since I can't do any contraction, I have this everywhere. So the degree must be at least this C tau, and then Marcus, then I'm actually in this case. Okay, so this was the branch where we always have the pattern. What happens here? So it's not true that if you can find a contraction sequence like this, you don't have a pattern. You could take a pattern which is just increasing sequence, and yeah, that's not very hard to find. You can have a very nice permutation and still have this pattern. But what you can do with this, and this part I'm not going to explain the proof, is that there is a dynamic programming algorithm to test the pattern. I mean, okay, so the algorithm does exactly what I described here, but with the assumption that you have a contraction sequence. And this helps a lot. It's a bit like tree width. When you have a tree decomposition with bounded width, you can use it for algorithms. It's a bit the same somehow. What you do is try to find your pattern, but you only need to look at k parts at a time. And you don't even need to do every combination. Like if you had to do every combination of k parts, that wouldn't solve it. It would not be FPT. But you don't need to do that. Somehow, what you have is like this is bounded degree. You can think of it as a graph with bounded degree, and you only need to look at connected components of size k and try to solve sub-problems inside that. And this is FPT. Okay, I won't give more details about this, but this is the extremely nice idea of Guillemot-Marx, and this is what we now call twin width. Like having this contraction sequence. Any questions about that?
You need to know the contraction sequence. Or
Yes,
you do that.
here I have an algorithm to find it.
In
Yes.
this case.
Yes, that's the big problem for graphs, but for permutation you can like not compute it, but you can approximate twin width, so it's not an issue. Okay, so okay, I'm supposed at some point to talk about some results that I contributed to, so let's start doing that now. So if you remember in the beginning, I talked a bit about composition of permutation and then completely forgot about it and just did patterns. So let's put permutation, composition back in. So here's a fun lemma. Well, the informal statement would be if you have two permutations which avoid patterns, then the product also avoids the pattern. So if you want a more precise statement, it's for any patterns tau1, tau2. If you look at the class avoiding tau1, you multiply by the class avoiding tau2. So like that, every product of them when it's well defined. This also avoids the pattern. So it's not true if I avoid tau and tau, it's not true that the result will avoid tau. Because with product you can start from a small class of permutation, avoiding a pattern, and end up with everything. But here the new pattern which you will avoid will be more complex, larger, but there still exist ones.
You're saying there's some pattern
Yes.
which is avoided by that, right?
Like pattern f of tau1, tau2. So this lemma is very annoying because it looks extremely simple, and I don't know a really simple proof of it. So here's one which feels silly to do, but it works very well, but it feels silly. So first remark is, if you take this product, it is closed under patterns. That's quite simple to check. And now,
Well, what do you mean close on the?
so if you have sigma which belongs to this and tau which is a pattern of sigma, then tau is also in this.
Ah.
Right, the same way that we say close of the reduced graph for graphs. Okay, and what is the number of permutation of size n in that? Well, I know that in this class it's exponential. That's the Stanley-Wilks conjecture, which is not a conjecture anymore. It's proved by Marcus-Tardos. And same here, it's exponential. So like this, let me write the growth in red. This would be less than some constant C1 to the n, less than some C2 to the n. So this will be less than C1, C2 to the n, which is not factorial. So my class does not contain every permutation, but it is closed under patterns. That means it avoids the patterns. I don't have a much better proof of this. I have one which uses twin width in a non-trivial way. Like you have to again use Marcus-Tardos inside that proof. So yeah, I don't know if it's a nice one. It might be a very nasty question. Is there a simpler proof? I'm not exactly sure what I mean by simpler, but I'm not entirely satisfied by this proof somehow.
You said you have another proof. Does the other proof give you some idea what is f of tau 1, tau 2?
Not much better. Like this, okay, there's a nice thing about permutation, which is that there are universal patterns, which is you can make a permutation of size k squared, which contains every permutation of size k. So this gives an upper bound on the side of my pattern. So in a stupid sense, it gives me a concrete pattern which this avoids. It's not very satisfying. The other proof is basically the same. Like the result is the same. I have a bound on the side of the pattern. I can't say something much better than that.
So without Marcus-Tardos theorem?
Yes,
no
but
proof?
like somehow this is what I want to say. Can you prove this without using Marcus-Tardos? Of course, that's not a very well-defined statement. But okay, but let's this. So now my result, like it's not just mine. So this is something we did with Edouard Bonnet, Romain Bourneuf, and my advisor Stéphane Thomasek. And it's last year, let's say. So here, okay, you remember the separable permutations at the beginning? I'm not sure if they are, yeah, they are still done there. So the co-graph of permutation. So let's write S the class of separable permutations. So this lemma tells me that for all k, if I look at S to be k, so like S and I make product of length k of separable permutation, this avoids the patterns. while we prove the converse. If you have a class C of permutation avoiding a pattern, avoiding a pattern, then there is some constant k, such that C is in fact a subset of product of length k of separable permutations. So, again, if you have separable permutation, if you allow unbounded product, you will get every permutation. In fact, you only need length log n, and it's like a big O of log n. It's just a sorting algorithm. If you bound the length, then you avoid the pattern. But if you take sufficient length, you will get every possible class avoiding a pattern.
So in which sense, like if you compose like log n times, it's a sorting algorithm?
If you do a merge sort, well, the merge operation, so it's not separable, but you can write it as a product of two separable permutations. And if you do merges in parallel, it's still a product of two separable permutations. And parallelized merge sorts, you have log n depth. Okay, I won't talk really about the proof because I don't have time and it's horrible. It's quite funny because it comes from coloring. So, okay, twinit, I say that this is twinit for permutation, but then the name of twinit comes from the generalization to graphs. And there's a theorem which is that if you have a class of bounded twinit, then it is polynomially chi-bounded. Like the chromatic number is a polynomial function of the clique number. So this was proved by Marek Szafowski and Mirko Pilichuk proved it for quasi-polynomial bound, and then Romain Bonneuf and Stéphane Thomasé improved that to polynomial. And okay, of course, coloring or you can't apply it to permutation, it's not something about permutation, but the proof uses a quite complex decomposition where somehow you take a graph of twinit k and construct it from graphs of twinit k minus 1. And this decomposition, this is very general. It's not just about graphs, it works for any structure for which you can define twinit. And when you look at it for permutation, you think about it a bit, there are simplification, lots of stuff, and you end up being able to express it with these direct and skew sums from separable permutations, and a bounded number of products. And then you reorganize this a bit, and you end up writing it as a bounded product of separable permutations. Okay, I don't want to say more about the proof, so let me just give some nice question about around this. Let me check this. Oh yes, so I had first one was, okay, I mentioned algorithms, and in particular this Guillemot-Marx algorithm in linear time. One important thing to point out is when you have this algorithm, you assume that the permutation is, you don't give it as an array where you have a non-trivial sorting problem. Like, I don't want you to give me an array of arbitrary numbers and say this is a permutation. I want you to give me, for instance, an array with just numbers from 1 to n, which is something for which sorting is easy. So there was I had a question which is, can you sort in linear time an array which avoids the patterns? So it's not a question anymore, as you can tell from my use of past tense. It has been solved very recently by Miral Hoppler, like 1 month ago. So it's a very nice algorithm. It again uses Marcus-Tardos. Doesn't use twinit, which is a bit disappointing for me, but it's still a very nice algorithm. Okay, so not a question, whatever. Next one. What did I write? Oh, yes. Next one is pretty much is very related to this, which is can products help to find patterns? Okay, that's not a very precise statement. Concrete question, I give you a product of two separable permutation. Can you test if there is a pattern in that product without just using the Guillemot-Marx algorithm? Can you do something which uses the fact that it's a product of two separable permutations? And yeah, I think this is pretty much the same thing as this. What I'm really asking is, can you understand what is the relation between product and patterns? Last one, something which Stefan likes a lot, is can we generalize this to matrices? By which I would mean, can you find some like basic class of matrices from which you can generate any class of bounded twin width by a bounded number of products, and I suspect that for matrices you would also want sums of matrices. There, of course, there might need to be adjustment to this statement. And yeah, that's all I wanted to say. Thank you very much for your attention.
Thank you. Any questions?
So in the first question, is there some how is the dependency on the pattern?
Sorting
Usual
Yeah,
FPT.
I see.
Yeah.
Is there
I
some
think
lower
it's not a
bound?
nice function that will be some.
Right.
A lower bound, you mean depending on the dependency on tau?
Yeah.
I don't know.
And the exponential dependency, is it unavoidable? So is there like
Explain
so yeah, you said that it's FPT algorithm depend.
Wait.
Parameterized by the size of
No,
the
wait,
pattern?
what am I? No, I need to check. No, actually, there was something surprisingly good. No, it's not exponential.
Ah, okay, so it's putting
Because there's the exponential from Marcus-Tardos, but then his algorithm somehow has a logarithm of that exponential. I need to check, but it might be polynomial in
Okay.
tau as well.
Okay.
But isn't lower bound trivial? The lower, because if I forbid 1, 2, then this class of permutation contains only the inverted one, right?
Yes.
But you still need the linear number of swapping move.
I mean, of course, we can do better than linear. I think
Yeah, yeah,
John
yeah,
was
yeah.
asking what is the lower bound on the function of tau.
Yeah.
Oh, so this is running time. Oh, so when you say sorting in something, that means that's running time of sorting. Right?
Yes.
Can you do
So-
it faster than linear time for sorting?
But you have to read them, right?
Oh yeah, that's right. So
Yeah, so
linear is
the
always.
linear, so the lower bound was about the dependency on the pattern.
Oh,
The result
I see,
says
so that
this
hidden
is
one.
that you can. Yeah.
Mm.
Oh, so are there generalizations of the Stanley Wolf? If you forbid more than one pattern, you get polynomial size, things like this, or?
So there's the thing like separable permutation, I consider them to be very, very simple as far as permutation go, and it's already exponential. So a class which would have polynomial growth would be extremely small from my point of view. I can't really think of a good example. But it seems unlikely to be that you would have non-trivial results, like you avoid a few patterns with some condition, and then the growth would be less than exponential.
So you said that the proof of this theorem is obtained from the toolbox used for proving this polynomial boundedness. So do you think it makes sense to and you analyze this toolbox and how it works on the permutations? Do you think there can be like other objects that where the toolbox will lead to some like a neat theorem like this?
Yeah, can we do something else with it?
Have you considered some candidates?
No, I don't have good candidates for other theorems to prove with that. It's okay, in the case of permutations, when you write it like this, I have a nice converse lemma which says you can go beyond the bounded limit with these tools. That doesn't work with graphs. Like if you take the condition of the decomposition, you could also have graphs with unbounded limit which would have this. So it's a bit harder to use with graphs in general than permutations. But yeah, no, I don't have a good candidate. That's a very good question.
So initially the tool is like stated for matrices.
Yes.
Right?
All right. Any more questions? If not, let's think that.